string and a duster. Now, I've chosen a duster because it's not going to hurt too much if it hits you too hard. So to make it go around a circle,
I'll take my glasses off.
I can start, I apply a force through the string. So which way is the force acting on the duster?
The torsion motion.
It's going circular. So at this point, when it's here, which way is the force being applied on that?
Clockwise.
That way.
No.
Clockwise.
Anti-clockwise.
Down. Clockwise.
Force is going.
No.
Left, right.
All right, have a think about this. Now I'll show you, I'll give you something, give you a hint. I'm going to let go of it at the bottom of its motion. Okay? And you can just grab it out for me. It goes at a tangent. So its velocity, or the speed it has, constantly wants to go straight. If I let go of it going upwards,
It's going to go up.
it's going to go almost straight up. I didn't let go of it straight up.
I'll just stay up here.
So, yeah. It means we have a circle. At that point in the circle, you draw a straight line out.
What happens
That's
if
a
you want to
tangent.
get it to go up to around there?
So,
Not hit that at all.
yeah, absolutely. So this thing's going in a circle at the moment. At any point on it, I let go, it will want to go in a direct straight line or a tangent to where I let go of it. So obviously it has a speed that it wants to go off at any point. Okay? But what is forcing it to keep bending around? Don't use the name, it's just what is causing it to keep going in a circle.
Your hand.
Not my hand is the string. And which way, if it wants to go that way, what is the string doing? It's pulling it back
The other way.
in another way. So there must be a force acting inwards down the length of the string, isn't there? A tension force. So the reason you get circular motion is because there is an inward force towards the where?
So that's sort of similar to the orbit.
Towards the centre point. There's a force towards the centre of motion or the centre of curvature. Get ready. Okay. And if it isn't there, it just goes in a straight line. Now it had a slight curve because of gravity, but yep.
So does that mean, like, if you put one of those Newton things, like, you know, that measures the newtons?
Absolutely.
So if you put one of those on the string, that
We'll measure a force.
force will be equal to the amount of force that it's going that way out.
That's right, exactly. Spot on, yep.
So those, all that kind of stuff is similar to the orbit of the planet.
It's identical to it.
Yeah.
In fact, we do that in the next topic. Now, the other thing about this is the inward directed force we call the centripetal force, not centrifugal. The force that is keeping this going in a radius is centripetal force.
But that centrifugal force is the tension force on the string there,
Is the tension force of the string. Now, the thing, I'm going to explain this in more detail in a minute, but the thing is, centripetal force means any force acting inwards that keeps something going in a curve. Ready, Riley? Yeah, I'll give it to you again. Here we go, so we can get the go. That's pretty good, and that's pretty straight.
Maybe
That would be the last time I do
aim
it.
up there. See if you can get it accurate enough to aim it about that area there.
Why? So I can crack it on the ceiling and wreck my duster.
No, just so you.
Whoops!
So you can't hit the camera.
Oh, right. Okay. No, don't do. Oh, he's going to do it back to me. That's dangerous because I can't catch.
I better not.
Okay. So,
Racing on the side.
whenever you see something going in a circle, there is a force acting inwards at the centre of the curvature, and it's called a centripetal force. But you guys heard of this stuff called centrifugal force, right?
Centrifugal force is what
Now,
produces it out.
centrifugal force. Here's my water.
Has that got any water in it?
It's got water in it. Who's going to wear it?
Mate,
Okay.
Let's go outside. Let's
No,
go outside.
it's pretty simple.
should we go outside?
No, it's all right. So if I do that, I can keep the water in it quite happily. The trick is to stop it down here, not up here.
Really?
Yeah, if you get in the wrong spot and you hit a fan, it's really disastrous as a demonstration.
Can we try stopping
Right.
it in the wrong spot out there?
No, 'cause you'll get very wet doing it. Now, so the question is, what's holding the water inside the bucket? Now, think about this. As the bucket goes round, why is it going in a circle? Why does it keep going
So you
round?
keep pulling it in a circle.
Because there's a centripetal force acting inwardly on my arm, a tension force, dragging it around. But what does it actually want to do?
Go out.
Go straight line. right? What does the water in the bucket want to do?
Go out.
Okay, what's holding the water in the bucket? The bucket. So the water's trying to keep going in straight motion, but the bucket is in the way, it can't. So the inertia of the water, the desire to keep, and I'll use the word desire very roughly, but the desire to keep going in the direction it wants to go keeps the water in the bucket because it's trying to go out there and the bucket's holding it back. When I have it straight up, it's trying to go that way, but the bucket's in the way, it holds it in place. So there's a contact force between the water and the bucket, but there's no force pushing the water out, it's just the desire of the water to keep going in a straight line, just holding it there. But there is this thing called centrifugal force, and it looks very real, but it's actually called an imaginary force, or an unreal force. Now, so imagine this, you have to think about it in these terms. And this is a bit of a thought experiment, and go with me on this one, all right? Imagine you're in a bus. It's pitch black at night. You're in a bus, pitch black at night, and you're sitting there, and it's on a frictionless, perfectly smooth road.
So we're on ice.
And you're reading, no, you're not on ice because it needs to be this frictionless road. This road, even though it appears to be frictionless, it still has enough traction to make the bus go and turn somehow. So it's a bit of a thought experiment, a bit magical. So we have there, let's say Riley's sitting in the seat reading his book, and being the gentleman he is, Marnie has to stand beside him reading her book because there's no other seats.
So
Right. And as the bus, unknowns to you because it's a very, very smooth bus, goes around a corner. Now, you're quite happy, you're reading your book, but you notice out the side of your eye that suddenly Marnie accelerates rapidly, hits herself on the other side of the bus. Not quite, it wasn't that bad.
Because he's on meth.
Yeah. Now,
He's on ice.
Riley, being a good physics student, looks up and says, oh, look, Marnie's accelerated. And of course, having accelerated, there has to be a force. I know, we've gone around a corner and she was accelerated outwards, so she's had a centripetal force.
What normal people doing? Oh, you're
Right.
okay. Oh, she just accelerated because we ran a corner.
Now, before you answer that,
How does the bus turn the corner if it's on?
that's why I said it's a good thought experiment. Now, the thing is, Brad in the space station, who happens to be looking out overhead with his spyglasses through the bus, notices that the bus actually does change course compared to the Earth and go in this nice arc. And he sees Marnie fly across the bus and hit the side wall while Riley happily sits there because the friction between his pants and the seat holds him there. You being a sensible, you being a sensible physics student from the space station, being an astronaut, you look down and say, right, the bus has experienced a centripetal force which made it turn, wheels to ground, but Marnie, because she wasn't secured, her inertia has made her fly across the bus until there's a contact force with the side wall, and that stopped her. So there was no force, it was inertia that made her keep going. Okay? So the reason we say there's a centripetal force is because from Riley's frame of reference, the only way you can explain seeing Marnie accelerate across the bus is there's a force. But for you, from your external view, in another frame of reference, looking down on her, understands that it's actually inertia that's doing it. So with it's like the bucket. If you're outside the bucket looking at it, we can work out the bucket is holding the water in place as it tries to move against the bucket, right? But if you're inside the bucket going with it, all you can see is the water is continually being accelerated. It'll actually change its position in the bucket slightly as it goes around. And you say, it's being accelerated back and forward from inside the bucket, so it appears there's a force moving, working on it. Hang on, I've got two questions. The one that holds the space station in place is centripetal force, because it's going a circle. If you cut gravity off, it'd go off in a straight line. So there's an inward force towards the centre of the Earth, right? But if you had something in there that moved freely of the space station, it would just drift out into the wall, and you'd say, oh look, there's a centrifugal force acting. That's what it would look like from inside the space station. When you move out of it to another reference frame, you can see it's inertia acting. So centrifugal force is from inside the reference frame saying there's an acceleration, but from outside it's inertia working. Okay?
Yeah, so I understand.
We've got a question here first.
Oh no, it's right, everyone asking about it.
No, go. Your questions are important.
So if you're inside the bucket, would you actually feel anything? Like say if, because you know how the Earth's moving and we're just sitting here, it feels normal. But like, would it be the same sort of thing?
I'll tell you what it feels like, and it's really weird. No, it is. I've been in a ride where what you do.
those rides where they spin around.
There's a big cylinder in the ground, and it spins. You stand against the wall, and it spins really, really quickly, and then they drop the floor out from underneath you.
That's in Luna Park in Sydney.
Yeah, and when you do it, it's really strange what it does to your senses because you know you're standing up, but as it goes faster and faster, you actually see the sky move until you feel like you're lying down. Right? Even though you know you're standing up, your senses are affected and you feel like you're lying down. And then you can do anything. You can, even though you're flat against the wall, because you feel like you're lying down, you can happily spin on it and do all this sort of stuff. The only thing you can't do is get up from it. Because if you sat up, then you'd get head first and they tell you don't do that. But then when it slows down again, trick one, don't be upside down. But you feel yourself coming back to the upright position.
How does that even start? Like everybody, okay, we're in the room, and it starts spinning around.
You can see everyone.
If you were very talented, you could like roll over onto your front and just stand up. You'll be.
Your centre of gravity guarantee you'd go head first in the ground. Yeah, centre of gravity. So what I am going to do for you guys, I will give you some more formal notes about this, but I just want to talk through the equations and how they work. So as I said, if you have an object going in radial motion like that, circular motion, there is going to be an inward force, which we call the centripetal force. Now, the thing I have to say is there's no such thing as a centripetal. Okay? So when I was swinging this around, when I swing this thing around,
Do I have to get up and cash?
no, I won't do that. Even though I can use the centripetal force formula on it to do some calculations because it's going in circular motion, I know it's not a centripetal that's making it go around circle. It's string and it's a tension force. Now, Riley's quite keen on asking about things going around the Earth. We can use centripetal force formula to work stuff out with it, but it's not a centripetal holding it there. It's what? Gravity.
So what's an example of the true
Centripetal.
So
Anything that's going to circle has got a centripetal force being applied to it. One that's pointing to the centre of motion and making it go in a circle.
if it always wants to go out, how is there always centripetal force?
Well, the centripetal force is what's making it. At that moment, it wants to go that way, but it's pulling it in.
Yeah.
At any given
that's
point.
The string. You said that's
Yeah.
not a real example.
No, what I said is there's no such thing as a centripetal. So even though the centripetal force formula works for that, the thing that's holding it there isn't a centripetal, it's a string.
So what is a centripetal?
It just is any force that holds something in a circular motion.
So it is a centripetal.
Right, I'll try it again. We can use the centripetal force formula to calculate what's going on. Because it's going in a circle, we call it a centripetal force.
Yeah.
But there's nothing that is a centripetal in terms of I'm pointing at that and saying that's string. It's not a centripetal. You know, it's not an object or a thing. It's not the cause of the motion, in a sense. So that gravity does it, or an electric charge does it, or a magnetic field does it, or a piece of string does it. But
Why do we call something centripetal?
because this formula,
How long is this?
sorry, I've got a lot of questions. I'll come back to those. This formula, the centripetal force equals the mass times the velocity, instantaneous velocity squared over the radius, will work for anything that's going in circular motion. But equally, if I want to work out, say, the gravitational force acting on a thing orbiting the Earth,
Think about the V, does that mean that's effective?
it equals, yes, formula for gravity, which you'll learn next term, is this thing. Right? That force there is a measure of the gravitational force that's holding the satellite in orbit. That there will equal that there. Why? Because that force, that's the size of the force that's holding it in place around the Earth. But if you want to actually do some work around gravity, you'd use the gravitational force formula. That one works for everything that's going in a circle, but it only tells you about the mass, the velocity, and the radius. This one works specifically for gravity. If you're dealing with force to do with charges, there's another formula you use. If you're dealing with force due to magnetic poles, there's another formula you can use. And I was going to go into that with you in a second about these things.
So they might centripetal is sort of like a general sort
It's a general term. Yeah, that's all it is.
The other thing is is the eraser on a string centripetal or centrifugal?
Okay. Centrifugal, remember, is centrifugal is the example of the bus where you're in a closed-in reference frame and something is accelerated next to you, and the only explanation you have is there's magic force acting, and you know you've gone around a curve. So it only applies inside that frame. For me to see a centrifugal force on this, I'd have to be inside the duster. 0.1 of a kilogram, right? And yep, and it's going around a circle, and let's make up a speed. Now don't forget, this velocity is its instantaneous velocity. The speed it would have if it went out in a straight line at a tangent at that point. Okay? So let's imagine that was going around at 10 metres per second. It's just a number. And what radius do you reckon that the string was?
Half a metre.
All right. So my radius is 0.5 of a metre. So when I want to find out what force is acting on that particular thing, I just put in the 0.1 kilogram times 10 squared metres a second. Should be all squared. All over 0.5. So when you do that, that's going to be 100 times 0.1, which is 10. 10 divided by a half, 20. So there'll be 20 newtons of force acting on that particular duster to keep it going around a circle. Okay. Now, on top of that, I feel tethered. It is actually, in that case. It won't always be. What's it going to be dependent on?
The speed at which you spin it.
And the radius is going around that.
Centripetal or centrifugal?
That's centripetal. This formula is centripetal. Pulling in.
So that's finding the strength of the duster.
No, it's finding the force applied to the duster to keep it going in that circle. Let's actually do a real problem or question here. Here's the Earth. And above the Earth somewhere is a satellite. And the satellite is travelling around the Earth at a constant radius. And it has a mass of 1,000 kilos, which is not unreasonable for a satellite.
That's a ton of satellites.
It's a ton of satellites. And it has an orbital period of 4 hours. Actually, let's make it 6. We'll make it a slow satellite. So go about 6 hours. Okay? Now,
Is that slow?
given that the diameter of the Earth plus the distance, the radius of the Earth plus the distance to the satellite is r. So from there to there is 6,360 kilometres.
It sure is, I think.
Plus another, let's say, 200 kilometres out to where it is. So we'll make that 6,560 kilometres. Okay? Please don't do that. So what force is acting on this satellite? Now, centripetal satellite, the centripetal force is going to be the mv squared on r. Now, what's the hard part in this formula to work? The velocity. But the velocity is going to be the distance travelled over time. Now, the distance travelled is going to be pi r. Is it pi r squared or 2 pi r?
2 pi r series.
2 pi r, isn't it?
Yep.
So now what we get is equals m 2 pi r all over, that's squared, and that's got to be over the time, and that's all over the radius. Okay, does that make sense to everyone? And this is a sort of question which will typically turn up in exams and HSC exams. You go into the space topic. Right, so if you do that, you're going to end up with 1000 times 2 times pi times 6560 times 10 to the 3. Why 10 to the 3?
Because that's 1000.
Yep. No, it's 10 to the 3. Why?
10 squared to 100.
It's in kilometres, and I need to make it metres. And that bit there is all squared. And then it's going to go over, 6 times 60 minutes times 60 seconds for the time. And then the bottom half of the equation
Which
is going to be over that, which is 6560 times 10 to the 3, because we're doing metres. Because force.
Why change the formula from mv squared to m2 pi r squared?
Because 2 pi r is the distance it travels over that time of 6 hours.
That's the velocity, is it?
That's the velocity. Okay? Actually, what I have to make sure of course, is the squared bit is that bit. Can someone just, if you want to do that in the calculator, we'll find out the force acting on it.
Jack, you with that is dangerous. Stop.
It's 10 to the 3 squared, all squared in the brackets, isn't it?
It's 2 times pi times 6560 times 10 to the 3 divided by 6 times 60 times 60 all squared.